Welcome, this is the first video of a playlist about the preparation of alkenes. In this first part, we'll have a look at the beta elimination of hydrogen halides and sulfonic acid esters. This reaction has been thoroughly investigated and many variations are known, but I'll limit myself to the most relevant. In parts 2 and 3, the dehydration of alcohols and the elimination of amines will be discussed. In part 4, I'll show you examples of the preparation of allylic alcohols by ring opening of epoxides. Part 5 is about the alkylation, arylation and acylation of alkenes by substitution of vinylic hydrogen. This includes oligomerization and Heck reactions, but also the Friedel-Crafts acylation of olefins. In the last video, I'll show you some strategies to convert alkynes into olefins. For instance, partial hydrogenation or alkylation. Throughout these 6 videos, I'll call compounds with a CC double bond interchangeably alkenes or olefins. There are many more ways to prepare alkenes. The most important strategy is the olefination of aldehydes and ketones, and on my channel you can find several videos about such condensations. Also, the formation of enolates, enamines or enol ethers will not be covered in this playlist. The same is true for allylic substitutions, cycloadditions, carbene or ketone dimerizations, the isomerization or metathesis of olefins, and for the dehydrogenation of alkanes. Most of these strategies only enable the preparation of special types of compound and lack general applicability. First, some general remarks about alkenes. Those listed here are important monomers for the manufacture of plastics and are prepared on a huge scale. For instance, more than 200 million tons of ethylene were prepared in 2021, mainly by thermal cracking of fossil hydrocarbons. Byproducts of ethylene include propene and 1,3-butadiene, the latter being important for the preparation of synthetic rubber. Styrene, acrylic acid and acrylonitrile are manufactured by more targeted oxidative processes. To give you a better feel of these quantities, the amount of ethylene produced annually is more or less the same as the amount of beer brewed. Then, worldwide, people drink 3 times as much Coca-Cola each year and 26 million tons of wine. Alkenes are mostly used for preparing polymers or as synthetic intermediates, and are only rarely found as a structural element in pharmaceuticals or agrochemicals. Olefins are usually too reactive and therefore too toxic. One exception are fast-acting cyanoacrylate adhesives, which react quickly with water and other nucleophiles before reaching any vital organ. Alkenes are versatile intermediates for many types of product. Typical reactions include oxidations, addition of protic compounds, and alkylations, arylations, and acylations. Some of the latter will be discussed in part 5 of this playlist. The precise mechanism of beta eliminations depends on the leaving group, the structure of the starting material, and the reaction conditions. Eliminations have been categorized into 3 idealized types, but in the real world, eliminations will never conform exactly to any of these mechanisms. These are just extreme cases, helpful for understanding the observed selectivities and kinetics. In the bimolecular E2 elimination, deprotonation and departure of the leaving group occur simultaneously, ideally from an antiperiplanar conformation, as shown here. No intermediate is formed. I'll show you in a minute why this antiperiplanar conformation has the lowest activation barrier. Reactions that come close to such E2 eliminations could be the dehydrochlorination of simple alkyl chlorides. The E1CB mechanism describes the monomolecular elimination of poor leaving groups. It usually requires stronger bases and proceeds by formation of a carbanion intermediate. After a quick deprotonation, the rate-determining step is departure of the leaving group from the negatively charged intermediate. Typical examples would be the eliminations from compounds where R in this sketch is an electron-withdrawing group. The other extreme would be monomolecular eliminations of very good leaving groups. Here, the rate-determining step is formation of a cationic intermediate from the neutral starting material. A fast deprotonation of this cationic intermediate then yields the olefin. Typical examples include the solvolysis of alkyl diazonium salts or benzylic triflates, as well as most acid-catalyzed eliminations. The most common side reaction of eliminations is nucleophilic substitution, in particular for primary alkyl halides. Substitution can be suppressed with bases of low nucleophilicity and by increasing the reaction temperature. A high temperature usually favors elimination and other fragmentation reactions, and some eliminations do proceed just by heating, without the need of any acid or base. The activation barrier of bimolecular eliminations depends on the conformation of the starting material. In the antiperiplanar conformation sketched here, the electrons of the CH sigma bond are closest to the empty sigma star antibonding carbon-chlorine orbital, as indicated by the black arrow. During the elimination, the electrons flow from the base into the empty CH sigma star orbital, and those of the filled CH sigma orbital into the empty carbon-chlorine sigma star orbital to form the new pi bond. Because of this concertedness, even bases that are much too weak to deprotonate an alkane can cause eliminations. I'll show you examples in a minute. If a given starting material cannot attain a perfect antiperiplanar conformation, then bimolecular eliminations are still possible, but will just proceed more slowly. Before discussing specific examples, let's check some general reactivity trends. Particularly good leaving groups for 2-phenetyl derivatives are the heavy halides and dimethyl sulfide, while tosylates, chlorides or fluorides undergo elimination more slowly. Cationic leaving groups are also eliminated quickly from the highly reactive 2-cyanoethyl derivatives. The cyano group greatly facilitates deprotonation and thus elimination, what enabled here a better comparison of poor leaving groups. The relative rates given here, however, will not correlate perfectly with those of simple alkyl derivatives. In general, as a rough estimate, the more basic the leaving group, the worse it is. The anions of strong acids, on the other hand, are often good leaving groups. The structure of the starting material has a huge impact on the ease of dehydrohalogenations. Particularly good substrates include those with electron withdrawing groups in beta position, such as those of the previous two slides. If the newly formed alkene is conjugated with an arene, eliminations also tend to become easier. Difficult starting materials are those with an electron withdrawing group alpha to the leaving group. 2-alkoxy or 2-aminoalkyl halides, which would yield enol ethers or enamines upon dehydrohalogenation, also tend to be more resistant to elimination reactions. Here you can see how electron withdrawing groups in beta position enhance the rate of base-induced eliminations. A 2-chloroethyl ketone, for instance, eliminates chloride 10 orders of magnitude faster than ethyl chloride. Amides or esters are more effective than deprotonated carboxyl groups, but 3 to 6 orders of magnitude less effective than keto or phosphonium groups. These elimination rate enhancements correlate well with the acidity-enhancing effect of these groups. Nucleophilic substitution can compete with base-induced dehydrohalogenation. In this example, the less basic the phenolate, the higher the extent of substitution. Sodium nitrophenolate, for instance, yielded 83% of the ether and only 17% as styrene, while with the more basic 4-methoxyphenolate, almost 50% of styrene resulted. Thus, to promote elimination, strong bases of low nucleophilicity should be chosen. For instance, Terz butoxide, fluoride, or sterically demanding amines or amidines. Also, the choice of solvent can have an impact on the outcome of eliminations. Polar solvents can push a reaction toward a monomolecular process, for instance. Solvents also affect the nucleophilicity of bases, as shown here. Fluoride usually is strongly hydrated and mostly acts as a non-nucleophilic base. In tertiary alcohols or anhydrous DMSO, however, fluoride can become a good nucleophile. For simple bimolecular eliminations, solvent effects are only weak. As is the case for most organic reactions, aprotic polar solvents enhance the reaction rate, while non-polar solvents slow reactions down. This was also the case in this example, but the effect was small. I'll show you now some specific examples. First, of the elimination of primary alkyl halides without side reactions, then with side reactions, then of the elimination of secondary alkyl halides, and finally of tertiary alkyl halides. Primary alkyl halides are the most difficult starting materials because of their high tendency to undergo substitution instead of elimination. Here, this problem was minimized by increasing the reaction temperature and by using carbonate as base. The charge delocalization in carbonate diminishes its nucleophilicity if compared to, say, hydroxide or alkoxides. Here, a hydration or saponification of the cyano groups also had to be avoided, what precluded the use of hydroxides. Symmetric dihalides sometimes give acceptable yields of haloalkenes upon treatment with bases, as in this example. Again, the elimination was conducted at a high temperature, also to distill off the product and thus prevent twofold elimination. An excess of potassium hydroxide was the base, in combination with a crown ether and tetraglyme as a solvent. One convenient strategy for preparing volatile olefins or alkynes by dehydrohalogenation is to add the starting halide dropwise to a hot mixture of caustic and a high boiling solvent, and simultaneously distill the product from the reaction mixture. Even sensitive compounds can be prepared this way, for instance by condensing the product in a cold trap. Here, this technique was used for the preparation of 2-bromoallyl bromide from tribromopropane. This is another example of desymmetrization of a symmetric dibromide. Substitution with sodium thiophenolate followed by dehydrobromination with sodium ethoxide gave a fair yield of phenylvinyl sulfide. In this example, the dehydrobromination proceeded under much milder conditions than in the previous example because of the activating effect of the methoxycarbonyl group. Only one equivalent of triethylamine was used to avoid quaternization of the amine by the product. Mesylates and tosylates are generally more difficult to eliminate than bromides or iodides. In this example, the elimination was eased by the thiazole ring and proceeded smoothly already at room temperature. Nucleophilic substitution of isobutyl halides is slow because of steric crowding. In this example, an isobutyl type dichloride was dehydrochlorinated twice in good yield by treatment with an excess of fluoride and DMF. With potassium hydroxide, though, an epoxide was also formed. Tosylates are usually more difficult to convert into alkenes than alkyl bromides, as shown in these two examples. While a simple alkyl bromide mostly gave the terminal olefin when treated with potassium terzbutoxide and only 16% of an ether, the corresponding tosylate only yielded the substitution product. Alkyl chlorides are also slightly more resistant to elimination than alkyl bromides. In this example, with benzene instead of terzbutanol as solvent, the yield of substitution product was a bit higher than on the previous slide. With mixtures of potassium hydroxide and tertiary amines as base, the yield of alkenes can be enhanced a bit if compared to eliminations with pure potassium terzbutoxide. A quaternary ammonium salt was probably formed as intermediate. Treatment of the pure trimethylammonium bromide with potassium hydroxide gave the terminal alkene exclusively, without any ether or alcohol byproducts. LDA is a notoriously strong and non-nucleophilic base, but primary alkyl bromides yield large amounts of tertiary amine when treated with LDA at room temperature. With the still more basic sodium diisopropylamide and at low temperature, however, a high yield of terminal alkene resulted. To better understand the mechanism of this reaction, a deuterated 1-octyl bromide was treated with sodium diisopropylamide, and the expected deuterated olefin was obtained. The deuterated octyl chloride, however, yielded a mixture of monodeuterated alkenes, probably by alpha elimination, as sketched here. This result shows that even if a concerted bimolecular beta elimination is possible, this may not always be the preferred reaction pathway. Another potential side reaction of eliminations is the isomerization of the product. Isomerizations can be promoted by strong bases or by transition metals, as in this example. Here, a primary alkyl bromide was dehydrobrominated at room temperature by a mixture of dicycloxylamine, catalytic potassium terzbutoxide, and a palladium complex. No elimination of the tosylate occurred, but a mixture of two isomeric alkenes resulted. Also in this example, a mixture of isomeric olefins was obtained, despite the absence of palladium or strong bases. Dehydrobromination was brought about by an excess of DBU, which is often used for such reactions, despite its tendency to be quaternized. With the aid of enantiomerically pure bases, enantioselective dehydrohalogenations are sometimes possible. In this example, such a reaction succeeded with the potassium salt of N-methylephedrine as base. A long reaction time at low temperature was required. At high temperature, even primary alkyl halides can undergo acid-catalyzed dehydrohalogenation. Here, for instance, dichloroethane was converted into vinyl chloride by gas-phase dehydrohalogenation over a zeolite. The elimination of hydrogen halides from secondary alkyl halides is easier than from primary halides. But if the formation of isomeric alkenes is possible, mixtures will usually result. The less substituted terminal olefin is often called the Hofmann product because it is the main product of the Hofmann elimination of tertiary amines from quaternary ammonium salts. The Zaitsev product is the thermodynamically more stable internal alkene and tends to be the main product of the elimination of good leaving groups with weak bases. In this example, the amount of Zaitsev product increased when changing the leaving group from fluoride to iodide and by lowering the reaction temperature. Sterically demanding bases, such as potassium terzbutoxide, can also increase the yield of Hofmann product, as shown here. Still, a substantial amount of internal alkenes was also obtained. With an alkyl iodide and the sterically less demanding sodium ethoxide, a mixture of internal alkenes was the main product. Acceptor-substituted halides, like the starting material of this example, often undergo dehydrohalogenation only slowly. Here, the elimination already proceeded in refluxing ether with a triethylamine as base. In this example, iodide had to be eliminated from a structurally complex, sensitive starting material. A high yield of target olefin could be attained by oxidizing iodide to a iodoso group, which is a still better leaving group. Already at room temperature and at pH 7, a highly selective elimination occurred. Here, a ditosylate, similar to the previous starting material, underwent elimination by treatment with an excess of lithium isopropoxide. The initially formed enol tosylate, however, was cleaved by the alkoxide, and the final product was a ketone. Allenes can be prepared by beta elimination, but are not always stable and tend to isomerize to alkynes or 1,3-dienes. In this example, a vinylic triflate was converted into an allene by treatment with a bulky tertiary amine and 1% of a palladium complex. 7% of an alkyne was obtained as byproduct. Tertiary alkyl halides undergo elimination readily, often by intermediate formation of a carbocation. Eliminations become more difficult if this cation is destabilized by an electron-withdrawing group, as in this example. Hydrogen chloride could be eliminated from 2-chloro-2-methyl-cyclohexanone by heating with collidine or with lithium chloride and DMF, but yields were low. For tertiary alkyl halides or trihalomethyl groups, elimination under acidic conditions can be a more convenient strategy than base-induced elimination. Here, a trichloromethyl group was converted into a dichloromethylene group by refluxing with zinc chloride in acetic acid. Similarly, in this example, elimination of hydrogen chloride was brought about by strong heating with zinc chloride in dimethyl phthalate while distilling the product off from the reaction mixture. A few words about the dehydrohalogenation of 1,2-dihalides. Treatment with bases will usually first yield vinyl halides, as in some of the previous examples. In the presence of water, however, these are sometimes hydrolyzed to ketones. As shown in the second equation on the slide, dihalides can also be reduced to halogen-free alkenes by treatment with metals or some other reducing agent. Here, for instance, a 1,2-dichloride was reduced stereoselectively to the cis-alkene by heating with an excess of sodium iodide. As byproduct, first iodine chloride and then iodine was formed, which does not usually add to alkenes. Because the starting dichloride of this example can be prepared by chlorination of a trans-olefin, this chlorination reduction sequence enables the conversion of trans-alkenes into cis-alkenes. Here an alene was prepared by reduction of a 2-iodo-allyl bromide with metallic zinc. The aryl bromide remained unchanged. Like dihalides, also 1,2-disulfonates can be reduced to alkenes. In this example, a dimethylate was treated at low temperature with sodium naphthalenide, and the expected olefin was obtained in high yield. Let's check some potential side reactions. The most important ones are substitution and olefin isomerization, and I've already shown you some examples. Another one is the hydrolysis or base-induced cleavage of methylates. The methyl group of methylates is acidic, and strong bases can cause the cleavage of methylates by deprotonation and formation of a sulfene. In this example, a steroid-derived secondary methylate was stirred at room temperature with an excess of potassium terz-butoxide, but instead of the expected cyclohexenes, mostly the non-inverted alcohol was obtained. With the corresponding tosylate, elimination occurred to a larger extent, but still, a lot of the alcohol resulted. A reason for the low reactivity of these sulfonates was that because of the conformational stiffness of the steroid, no conformation with antiperiplanar hydrogen was accessible. When twisting the conformation from chair to boat, at one point, when all substituents are eclipsed, the leaving group will be syn-periplanar to one hydrogen atom, and elimination will probably occur from this eclipsed conformation. A perfect boat conformation with antiperiplanar hydrogen was not attainable in this case because of steric repulsion between the axial methyl group and the sulfonyl group. Another typical side reaction is the unexpected formation of cyclopropanes. If an alkyl halide or sulfonate has an acidic proton in position 3, then the cyclopropanes will form readily, and base-induced elimination may become almost impossible. Intramolecular reactions like cyclopropane formation are usually much faster than intermolecular reactions. Here, for instance, refluxing a concentrated solution of ethyl 4-chlorobutyrate with sodium ethoxide gave no ethers or olefins, but only the cyclopropane. Here are some more references which you can also find in the description of this video. For subscribers, there's a PDF version of this presentation under the Community tab. The next video of this playlist is about the preparation of alkenes by dehydration of alcohols. There you can find examples of acid or base catalyzed dehydrations, but also of a number of reagents suitable for dehydrations under milder conditions. See you then.